Think, Learn, Innovate.
Hi everyone, today we will be doing a derivation of Planck's radiation law. With the help of Planck's radiation law, we can derive other laws like Lorentz displacement law, Rayleigh-Jeans law, and etc. So in today's video, what we will do, we'll derive Planck's radiation law. So at first we'll say Planck's radiation law, what is his hypothesis and what is his assumptions. According to the Planck's radiation law, all bodies placed inside an enclosure can also emit black body radiation, and the atoms at the wall of the black body behaves like a simple harmonic oscillator and is oscillate with some characteristic frequency. These oscillators of the black body cannot have any arbitrary amount of energy, but it has a distinct amount of energy which is represented by nh nu. And so from there we can derive that. We will first say that let n be the total number of Planck's oscillator. Okay. E be the total energy. Okay. Therefore, energy per oscillator is given as, we'll name it an epsilon, and we call it an epsilon bar equal to total number of energy, and total number of oscillators. Okay. So let what we'll do is we'll say let or if n0, n1, n2, n3 dot till the last number of nn are the number of oscillator whose distinct energy is given as epsilon 2 epsilon 3 epsilon dot, and at the last you will get n epsilon. So overall we can write down therefore what we can say is the total number of particle oscillator, total number of oscillator actually, total number is n, that will be the sum of all the oscillator, n0 plus n1 plus n2 dot all of them. And similarly the energy E is similarly given as, first is 0, then next one is your epsilon n1, then 2 epsilon n2, then 3 epsilon n3. Okay, we have already know that these particles can be distributed, or that these particles, the number of oscillators with energy can be represented by Maxwell distribution formula. So we can say from Maxwell's distribution formula, we know that in another video actually I will give you the details of this Maxwell distribution formula. So I can call this one Nn is equal to N0 e to the power minus N epsilon by K2, where K is your Boltzmann constant. K is your Boltzmann constant. Now, so for this one, we can say for N0, what will be the value actually, and for N1 and N2. N0, if I plug 0, so epsilon will be 0, so it will be N0 same. So if I want to find out N1, then it will be given as N0 e to the power minus epsilon by Kt. If I want to find out N2, it will be N0 e to the power minus 2 epsilon by Kt. If I want to find out like this N3, it will be N0 e to the power minus 3 epsilon by Kt. So this is where the particles can be written with the help of Maxwell's distribution formula. Now, after you got the Maxwell's distribution formula, so we can substitute these values in your total particles, total number of particles equation. So what was my total number of particles equation? N was equal to N0 plus N1 plus N2, and like that it goes on. Okay. So here I will write on N equal to N0 plus first N1 gives me N0 e to the power minus epsilon by Kt. Then if it's N2 becomes N0 e to the power minus 2 epsilon by Kt. If I take another more term, it will be e to the power minus 3 epsilon by Kt, and like that it will go on. So what I will do now, I will take a common of N0, and I can write down this equation in this format itself. 1 plus e to the power minus epsilon Kt plus e to the power minus 2 epsilon by Kt plus e to the power minus 3 epsilon by Kt, and so on it goes on. Okay, and the last term actually will be e to the power minus n epsilon by Kt, which I will get. Now I will say let us introduce a variable, and we can take the variable to be any variable. So I will take it to be an x, and that x is equal to e to the power minus epsilon Kt. So if x is equal to e to the power minus epsilon Kt, if I plug this x here, my n is nothing else but N0 1 plus, what is this, x plus x square plus x cube dot 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 dot, and it goes on. Okay, so if it goes on like this actually, so it goes on a series, so it's an it becomes an infinite series. It goes on like this. So this kind of series can converge, because we know that. So I can write down like this. So any series will say I equal to 0 to infinity a to the power I, it will converge and it will give me 1 minus a. That's your convergence. Okay, so in this case also, so I will write down n equal to N0 summation of I equal to 0 till infinity x to the power I, and that gives me N0 1 divided by 1 minus x. Okay, now if I plug this value there, so I get n equal to N0, and then I get 1 minus e to the power minus epsilon by Kt, putting the value of x here, putting the value of x in the equation. Okay, so as it's infinite and it comes to like this, and this goes to n0 1 by x, and then I plug the values of x there. Similarly, I can write down the equation of energy in a similar form. So I will hit the energy now. What was my total energy? The total energy is given as, so E is equal to 0 plus, first one gives me epsilon n0 e to the power minus epsilon by kt. After that, what I got? 2 epsilon n0 e to the power minus epsilon by kt plus 3 epsilon n0 e to the power minus epsilon by kt, and it goes on. Similarly, what I will do here is I will take a common. What common I will take? I will check, see, epsilon is common in all the cases, n0 common in all the cases, and e to the power minus epsilon kt. If I take that, I get 1 plus 2 e to the power minus epsilon kt plus 3 e to the power minus 2 epsilon kt, and the series will go on. So similarly, in this series also, if I can take the same parameters as x equal to e to the power minus epsilon kt, so I get this equation like this, equal to epsilon n naught x, in bracket what I get, 1 plus 2x plus 3x square, and it goes on. So the convergence of this series actually gives you 1 minus x. So I can write down that series in this format, epsilon n0 x into 1 minus x to the power square. So now what I will get, if I plug the value of x here, I get epsilon naught e to the power minus epsilon kt, and I multiply 1 minus e to the power minus epsilon by kt square. So I got my energy E in this format, and in previous, actually in a previous slide already, if I go to the previous one, I got N. So I got N, as well as in this slide I got my E. So I have started with my formula epsilon like this is total amount of energy E divided by N. So if I plug the values of E here, E is a not e to the power minus epsilon by kt, 1 minus e to the power minus epsilon by kt square, that's, and if I divide it by n, and what is my n? If I go back, actually my n is n0, so it will be 1 by this value. So what I will get here, into n0, into n0 divided by not n0, it will be 1 by that, so it will be 1 minus e to the power minus epsilon by kt and divided by n0. So I will cut this n0 and n0 here, and this one here. So after this, what I will get the value? So see, I got epsilon e to the power minus epsilon by this. So if I go to the next one, I know my epsilon prime is equal to E, my n, and what I get the value here? Here I get epsilon e to the power minus epsilon by kt and divided by 1 e to the power minus epsilon by kt. Now if I divide by e to the power minus epsilon kt, numerator and denominator, I only left behind with epsilon e to the power epsilon. So if I divide this one, so if we were epsilon by kt minus 1. Now What is your epsilon? The value of epsilon is h nu. So if I plug this one there, so I got epsilon bar equal to h nu e to the power h nu by kt minus 1. Okay, and so we know that number of oscillator per unit volume within the frequency range of nu plus d nu. So we know that number of oscillators per unit volume within the frequency range of say nu to nu plus t nu, we know that is equal to, well, we did this cube by d. So that's we know, and so we have to find out the radiant energy density between frequency range of this one. So how can I find out the radiant energy? So the energy radiant is E d nu, and this E must be function of nu itself. That will give you the number of particles there with your energy. So what I get here, n is this value and epsilon bar is this one. So what I get here, 8 pi h nu to the power of cube d nu divided by c cube e to the power h nu kt minus 1. Okay, so with respect to nu frequency, so what we can find out? We can find out the value of the equation of Planck's radiation law, and this is your equation. So I will write down the equation in the next place in proper way. So as a function of frequency E nu d nu, the overall equation becomes h pi h nu cube d nu divided by c cube e to the power h nu kt minus 1. That's your Planck's radiation law, and I can find out this radiation law as a function of wavelength. So what is my wavelength actually? Wavelength, I can find out that word wavelength, and in case of wavelength actually, so how can I find out the value in case of wavelength? So first of all, I will write down the equation with respect to mu is equal to c by lambda, where lambda is your wavelength. Okay, so if I find out d nu, then what I get, c by lambda square d lambda. Okay, so this is your value, and I will take the mod value of this one, so I don't have to take the minus sign. So what I get, e lambda d lambda is equal to 8 pi h. If I want to find out nu cube, this will be what? C cube by lambda cube. Good. What is my d nu? D nu is into c by lambda square d lambda divided by c square e to the power h nu, and nu is equal h c by lambda kt minus 1. So if we do that, what we get here, this c cube and this c cube will go away, and the equation becomes 8 pi hc d lambda divided by lambda to the power of 5 ehc by lambda kt minus 1. So that gives you the Planck's radiation law. This is your Planck's radiation law. So if you like my video, please subscribe and I will bring all other types of derivation pretty soon. Thank you.